Hello, and welcome to our lesson on the properties of cyclic quadrilaterals and the alternate segment theorem. In this lesson, our primary focus will be on firstly understanding and proving that the opposite angles of a cyclic quadrilateral add up to 180 degrees, and secondly, exploring the alternate segment theorem and understanding its implications. Up to this point, we've built a solid foundation by discussing the technical vocabulary for a circle and how to prove angle theorems in circles, triangles, and across transversal lines. With this foundation, we are now ready to explore the proofs related to cyclic quadrilaterals and the alternate segment theorem. Let's get started. To start, we need to understand what a cyclic quadrilateral is. A cyclic quadrilateral is a four-sided figure, where all the vertices lie on the circumference of a circle. This type of shape is said to be inscribed in the circle. The first theorem we'll be looking at today states that opposite angles in a cyclic quadrilateral add up to 180 degrees. Let's walk through the proof of this. First, consider a cyclic quadrilateral ABCD inscribed in a circle with center O. Draw a line from O to D and O to B. Second, recall one of the angle properties we've covered before. The angle at the center of a circle is twice the angle at the circumference when subtended by the same arc. We can use this theorem to label the angle subtended at the center by arc AB as 2A, and the angle subtended at the circumference by the same arc as A. Similarly, label B and 2B for the opposite angle like this. According to our previous knowledge, the angles at the center, angle AOB and COD, sum to 360 degrees because they complete a full circle around point O. We can write this as 2A plus 2B equals 360. Simplifying this equation by dividing by 2, we get A plus B equals 180 degrees. You can see the angles. A and B are opposite in the cyclic quadrilateral, and we have shown that they sum to 180 degrees. We can do the same thing for angles D and B. Thus, opposite angles in a cyclic quadrilateral must add to 180. Well done, this completes the proof. The second theorem we'll explore today is the alternate segment theorem. This states that the angle between a chord and a tangent at the endpoint of the chord is equal to the angle in the alternate segment. Understanding this visually, this theorem tells us that the angles highlighted theta in the diagram are always equal. Let's walk through how we prove this. We'll begin with a circle with center O and a line EC meeting the circle at point D. Let BD be a chord of the circle and A be a point on the circumference. Let's now draw two lines OD and OB to form the triangle ODB like this. Let's also go ahead and label angle BDC as X, as we want to prove angle DAB is equal to X. Notice that lines OD and OB are both radii. Accordingly, triangle ODB is an isosceles triangle. Additionally, recall that the angle between a tangent and the radius is 90 degrees. Accordingly, angle ODC is 90 degrees. We can label this on our diagram. Notice that we can write that angle ODB is 90 minus X. This is because, together with angle BDC, it adds to the full 90 degrees. Also notice that since we're dealing with an isosceles triangle, we can label angle OBD as 90 minus X too. Since angles in a triangle add up to 180, we know angle DOB equals 180 minus ODB minus OBD. We can then simplify this to find that angle DOB equals 2x. Recall now our earlier theorem, which states that the angle at the center is double the angle at the circumference. Accordingly, angle DOB is x. Notice that we have now proved our theorem. Angle BDC equals angle DAB. Put into words, the angle formed between the tangent at point D and chord DB is equal to the angle in the alternate segment. In today's lesson, we explored the fascinating properties of cyclic quadrilaterals and the alternate segment theorem, enriching our understanding of circle geometry. First, we proved that the opposite angles of a cyclic quadrilateral add up to 180 degrees. This proof involved splitting the quadrilateral into triangles and using the sum of angles around a point. Next, we delved into the alternate segment theorem, which states that the angle between a tangent and a chord through one of the chord's endpoints is equal to the angle in the alternate segment. We demonstrated this by constructing triangles from the circle's center to the tangent and chord, utilizing properties of isosceles triangles and the relationship between tangents and radii. By mastering these concepts, we gained valuable tools for tackling complex geometric problems involving circles, tangents, and inscribed shapes. These theorems not only simplify our calculations, but also deepen our appreciation for the elegant relationships within circle geometry.